We are Team HHO, and we've been working on a water purification project to disinfect water via solar energy. The members of our team are Brendan King, standing next to me. He is a mechanical engineer. Nathan Lawrence, that's myself. I'm also a mechanical engineer. Francis Maikai, the general engineer, and Ryan Robinson, also a general engineer. So we started out by being given something by our client. We took what we were given by our client and we made a problem statement from it. The shortened problem statement that we're going to give you here is to create a water purification system using both heat energy from the sun and ultraviolet rays from the sun, using both. Just to be able to distinguish between those things. If you can see Appendix A, you can find the full problem statement. We shortened it to put on the slide, so you didn't have a mountain of text here on the slide. You wouldn't have to read through that. Basically, that was something very important that the client specified to us. Probably the most important thing is that the system be able to use both heat and UV. And this is illustrating some more of the goals that we got from the client. It would have to produce enough water, enough clean water for 5 households per day, which we estimated after doing some simple calculations would be around 40 liters of water per day. So we based all of our calculations on that. And we also needed safe bacteria levels. Also, those were specified by our client, Dr. Pontius. So he told us exact levels of bacteria, and he told us he would provide some for testing, so we could use that. Anyways, this is more about what our client gave us. He gave us specific needs, as we mentioned, the 5 households. Here are some of those minimum bacteria. We have to have 0 E. coli per 100 liters, so no measurable E. coli, and less than 1 coliform per 100 milliliters. If you guys don't know what coliform is, it's basically feces of some sort. So you don't really want that in your water at all. So we're trying to minimize that as much as possible to provide for safety. And our water source is specified to be a river or a lake. As another thing specified. There's more specifications in there. You can see Appendix B. All the appendices are at the back of the packet, behind the slides. So if you see Appendix B, it has our full client statement of work, which is what we were given at the beginning of the project. So that should make it all clear to you if you want any more details on that. The next thing we did, we had engineering requirements, standards, and constraints, which were just more things to narrow down what our project is and what we want to be doing with our project. As you can see, we have all kinds of safety constraints here, like burn caution. We don't want a child playing near the system to get burned, for example. That would be a terrible disaster that would reflect badly on us and on the school. We want it to be easy to operate. We want it to be able to be in any location that they want to move it to, easily movable. And then we also have some engineering constraints on the other side. But as I mentioned, we purify 40 liters of water per day. We have to use UV and heat in the testing of it. Hopefully we can distinguish between the two. And no tolerance of E. coli and coliform. So those are bad. And if you want to see more of that, again, you can see Appendix C in the back. That will show you all the engineering requirements that we have. And here's a few constraints. As I said, filtering 40 liters per day. We were given $1,000, and that's a budget not just for our construction. Because obviously construction will cost more. Since you may have to decide, oh, we don't need this, we're going to have to use something else. So we'll have to spend more on that. But hopefully when we get to the actual model for production, we won't have to spend $1,000 on every model we produce, because that's a prohibitive amount of money. So we're hoping to bring that down. And then we studied some patents. You can see the patent numbers and things here for some patents we were looking at. Because we want to do research and come up with something new and original and unique. So that instead of just copying what someone else does, we want to have a unique design feature. And again, you can see Appendix C for the engineering requirements, which I already mentioned. Now, what we did was we took our client's requirements, which we've just been over pretty thoroughly, and we did a customer needs analysis to decide what the customer would want, what would be useful to the customer. And we're under the assumption that our customer will be people in developing nations who don't currently have access to clean water, so we want them to have that access. And so we've got some important things here that we thought would make it easier for them. We want it to be easy to ship and receive for them, so that there's no complicated airplane drop where they have to get it, so they can put it on the back of a truck or some other form of transportation to get it to their community where they can use it. We want it to be easy to assemble, easy to use. It obviously has to be effective in water purification, since that's the main goal of the system. It needs to be safe, portable, easily accessible. The water inside is easily accessible. It shouldn't be incredibly difficult to get the water out, because we want to be able to use the water. And it also has to be inexpensive, so we hope to cut costs to lower prices to make it more available to everyone who might want to use it. Okay, and then we took those both the client needs and the customer needs. And we took those, we had to build them in the quantifiable engineering criteria. And not everything on here is quantifiable. Quantifiable means it has numbers. So we can actually measure what we're doing with numbers and say, okay, we haven't met this standard, we have met this standard. And so if you want to see more of that, you can look in Appendix E, which is our engineering criteria. And here's just a small sampling of that. We have an easy to transfer and low cost of shipping. And again, in the appendix, we have an actual number for that, of how low the cost has to be.
It's $50.
$50 for shipping, yes. And then we want it to be simple enough that a person, a 13-year-old, could assemble it after looking at the instructions. We don't want to do something that you have to have complex engineering knowledge or skills to assemble or understand. We want it to be pretty simple. Purification requirements are met. It has to be safe for children to be around so that a kid won't land underneath it and be crushed by the system. And we want an average-sized man to be able to move the system. So we assume a 150-pound man will be able to move the system, so we can't make it too heavy for that. And we want 5 minutes or less to remove all the water and reload it with new water so that people won't spend or waste too much time doing that. And now we're moving on to Brendan.
All right, so every design concept starts with an idea, and that idea grows over time as you experience more difficulties or come up with new ideas to branch off that one. So concept generation is a way to kind of start that idea growth process without actually starting to build it ahead of time. So our project had collaboration with a lot of different things that we offer here at school, as expressed by the circles around the main concept generation. So basically concept generation is starting an idea and then going off that before actually implementing any further things. One of our first things that we had to decide between was a static system or dynamic system. As you remember, last year we had a dynamic system start off, but after discussing with our client over break and trying to re-evaluate where we were standing at last semester, we decided we'd just start from fresh and really dig deeper into which of these two will work. So here, we decided to get really scientific and just do a pro and cons table for each system and just kind of pretty much weigh them out. As you see listed here, we have the static pros kind of outweigh the static cons. One of the main cons, though, that we were really looking at was finding a new innovation, since that was one of our things asked by our client was to come up with a possible patent idea. That was one of the strongest and why it's on the bottom, kind of like the heavyweight con that we had. And then we went ahead and just did it again for the dynamics. This one made it kind of simple. As you can see, there's a lot more cons to this than we originally thought of, but again, one of the pros was it's an easier way to find a new innovation. We ended up getting a possible innovation idea for our static one, which we'll get into later. But between these two, you can see that the pros on the static outweigh the cons, and the cons outweigh the pros on the dynamic. So with that scientific research, we went ahead and went with our static system. We then took a Gantt chart and kind of got a little step above just the pros cons table and actually took our concept generation charting ideas and did them as a collaboration of the two systems together using the Gantt chart here, and came up that although the static one was pretty stable in and as itself, the dynamic one actually had a negative contrast with the static one. So that kind of put the nail in the coffin on let's stick with the static idea and really dig into how we can apply our static system with a new innovation idea. We also did this with, if you remember last semester, we were debating on whether to use like an over-under type system or a serpentine type system for our dynamic one. And again, after taking them apart, we decided to go ahead and go with the static. So from concept generation then into concept selection, we get into a little bit more deeper. So now we kind of have our general, we're going to go ahead and go with the static, but now we're going to dig deeper into that. So the problem with using, the problem with concept generation is sometimes you don't get to use some of the ideas that you had in concept, in concept selection, you don't get to use some of the ideas that you came up with in concept generation. One of our main ones that Dr. Heckman and our technical advisor, Dr. Ricard, was working with us for was this heat control valve, to where if it was dynamic and it continued to flow through, water would not be put into a storage tank until it reached our specified temperature of say 150 degrees Fahrenheit. So that was something that it probably is not going to end up working out for us. The other thing was using the solar power for mechanical parts. If you remember on the pros and cons list, one of the cons on the dynamic system was that we were going to have some type of pump or way to continue water flowing and we were going to implement a solar power on that. So luckily, we don't have to worry about that in our static design. We then took a morph chart and took our concepts and compared them with each other on positioning, on the body style, on the materials, things like that. And as you can see by the circles, for the body system, we went ahead and had like an exterior wood box. This goes into one of our safety factors from before on burning. You can't really burn yourself on wood very easily. We're going to go ahead and go with a level plane. That way all the water is distributed equally amongst it. And then heating from the sun, and we're going to be using a black material, which we'll get into later. Some of the simple or easier heat transfer calculations that we did were basically for how does heat transfer between water, air, and the several materials that we're going to be using, including the insulator of the wood box around it. So that's what that is. One of the harder calculations that we did was finding out how big of an air gap insulator we wanted between the top level of our water and the top or the bottom level of the PET or plexiglass material that we'll be using for the UV. And it had this as distance between the water and the plexiglass increased. It kind of had a logarithmic asymptotic relationship. So we went ahead and went with 2 inches on that because it was a reasonable amount where as you just increased, it was getting bigger and not so easy to move. So that was one of the easier math calculations that we did for that. And then pass up to Ryan. Oh, Francis, excuse me.
Well, I'm Ryan right now. We're talking about the functional design right now. Just our whole entire process, breaking it down level by level. We're going to start with the innermost level of the purification system, which we take black acetyl clay, well, it's a plastic, and Ryan's going to explain a little more after me, like the properties and why we chose these materials. But right now, for the functional design, we start off with this plastic that we're going to build into somewhat of a trough. Well, it is a trough for our water, and it's kind of hard to see on here right now. It's not nice much of view, but these are 2 fins coming across, and we'll explain that a little later. But this is the innermost part of the purification system where the water will actually sit, become heated, and exposed to UV rays to kill bacteria and purify water. Level 2, we have a Artec insulation. It's a foam insulator to keep the heat within the system, basically, that we're going to put around the trough that we developed. And then proceeding from there, we have level 3, which is just our air system enclosure bin. Just right now made of plywood. We're almost to the prototyping phase to where we can test everything. It's nothing really aesthetically pleasing at the moment, but this is what the enclosure bin is going to look like. And then finally, the top level is the cover to encase the whole entire system. And this is made out of PETG, which is a polyethylene template plastic. But it's a plastic cover. Also, we chose between, we're going to test between 2 different types of covers. And Ryan's going to talk about that in a little bit. But anyways, the black strip also around here is a weather stripping to seal the case. And Brendan touched on it a little bit, but also there's going to be a air gap inside the system used as insulation. And on average, from like our calculations and stuff, it will increase like the temperature roughly 10 degrees Fahrenheit within the system. So with that said, here's a couple different views of the system. I didn't put it in these drawings, but we have valves that we're going to put on each end to drain the water. Drain the water out of the system, and then it's just right now we just reload with like buckets of water from wherever the water source is. Yeah, so Brian's going to talk a little bit about prototyping.
Okay, so to discuss prototyping, a lot of the presentations, thank you. Today, everybody thinks, prototyping, okay, you just build a model and then you test it. Well, prototyping is testing a concept or an idea, but there's a lot of different types of prototyping. I have 3 up here: form study prototyping, visual prototype, and then of course functional prototype, which kind of covers everything that everybody was talking about. Form study prototyping really gets into developing the features, not the function of the material. So you're really building something that is eye-pleasing, but then it also is the same dimensions or the size of your eventual prototype that you're going to build. Visual prototype, you're really focusing on the appearance, the feel, the texture, the colors, but you're not focusing on function. It's more features and function. And then functional prototype, obviously you're reflecting on the function of it, but you're also doing features too. Okay, so discuss a couple of the different pieces that we chose. This is black acetoplastic. Now the idea behind this black acetoplastic is we want the maximum amount of infrared absorption of the infrared rays. The way our system works, last semester we kind of decided we wanted a reflective material on the bottom, so the sun comes in and it reflects the heat back and it heats up the water. Well, that's not very practical. After doing some calculations, we realized that's not practical really at all. So the way that we're doing it this year, or this semester, is really through, the heat is being transferred straight from, the plastic is absorbing the heat, and then the heat is being absorbed from the plastic right into the water. And because of that, you're going to maintain a temperature differential is not going to be very high. So over the course of the time, over the course of the day, the plastic is going to absorb a lot of heat, and then the water is going to be, the temperature is going to raise evenly with the plastic. Okay, so the idea of the insulation, we really want the heat that's in the plastic to stay inside the system. We don't want it to go out externally. We want all the heat possible to go into the water, and the heat goes to path of least resistance. So you want it to go into something where you actually want heated. So the idea of the insulation is to keep all the heat as possible inside of the system. And we chose the RTEC insulation for a couple of reasons. One, it's very lightweight. Second, it's pretty inexpensive, and then it also has a very high melting point, so we're not going to risk it melting because it is in direct correlation or contact with the plastic. Okay, now the frame. So the idea behind the frame is really just aesthetic, but it's also to provide the support and all the structure needed to hold this system together. We're going to be supporting 40 liters of water, which is pretty heavy. So we need something that's strong, but also at the same time we want something that looks pretty good. So we were really deciding between aluminum or wood. Now, for us, both of them held the weight that we needed. Aluminum was a little bit more aesthetically pleasing, but when it comes down to budget, wood's a lot cheaper than aluminum, which can get very expensive. So we decided to go with wood. All right, so like I said, the crux is really the crux of our presentation or our project is really that filament or that cover on there. We decided on two materials for two different reasons. One is a plexiglass material, and the other is a PEG, which is polyethylene terephthalate. Gotcha on that one. Cover. The idea behind the plastic is it utilizes the maximum amount of penetration of the UV. However, on the downside of that, it also, over time, like you've seen water bottles or your headlights, they kind of fade, and then that prohibits the different rays of sunlight or ultraviolet or infrared to penetrate through. So over time, it wears out and needs to be replaced. On the other hand, plexiglass has an extremely long life. It'll last for a really long time. The only problem is even with the material we chose, the type of plexiglass that we chose, it doesn't always allow the maximum amount of UV penetration possible, which is something that we have to have. So for us, it's kind of picking the better or the less of two evils, if you please. And it also, you can swap out the cover on it based off the situation. So if you're going to have a lot of UV penetration for if it's cloudy or such, you would want to go with the PET. But if you're really focusing more on the sunlight heating aspect of it, you'd like to go with the plexiglass because that way it doesn't wear out the PET quite as fast. Okay, so like I said, prototyping, we're doing functional prototype, and because of the constraint we have with our budget, our different materials, plexiglass, the PET, and then the black acetoplastic, they're all very expensive, and so we decided to cut our system down to a half-scale model, which provides, it's not perfect, but it's almost a perfect ratio of time and temperature for the purification system. So that way we could save some money on that. And then our complete parts list, these are only 3 of our aspects, but our complete parts list is on Appendix F of your handout. And currently our team progress, we have all of our parts, and we are hoping to actually begin construction tomorrow. And we have, I'll show in our Gantt chart here in a couple slides, but we actually have a milestone coming up on Thursday. We would like to do our first testing for our full first scale testing. So hopefully we can meet that. If not not this Thursday, hopefully by next Monday we'll be able to do that. Oh, that's our predecessor. Okay, so well-managed project, there's two main aspects of that. Work breakdown structure, work breakdown chart. We also included a work breakdown table. We found that to be a little bit better, and then a Gantt chart. So for our work breakdown table, on the right are just two examples. The one on the left is a work breakdown structure, which doesn't provide quite, it's just for, it's not the content, it's just for the idea behind the detail. Work breakdown structure doesn't really provide as much detail as we would like. So we went with a work breakdown table, which allows us to implement a lot more detail into our design and to cover all of our bases. So the five major important points that we have for our work breakdown table are water source, like we covered in the beginning, kind of where's the water coming from? Is that a lake, a well, a tap? Treatment, UV, solar, infrared, using heat. Our type of equipment, which was dynamic system, static system, how are we going to determine that? Some different constraints that we had, and then also extraneous aspects, which were important. That's where in the globe, or where on the globe are we going to use our system? Optimal daylight hours. How much time, are we going to have a day with the amount of intensity of sun? So that's kind of something we can't control, but it's something that is extremely important in our project. Okay, and then our Gantt chart, and this is just a little snapshot of what we have, and the whole thing is on Appendix H. But you can see here in yellow, it's a little pixelated, but this is our first full test for the entire day. So simulation, and of course it's going to be out there for almost the entire day. And you can see by the line, that this is today, and then we're hoping on Thursday to do that. But like I said, if we're not able to meet that, then we're hoping by Monday. But as of right now, we are pretty much right on track with where we need to be. Any questions? Daniel Young, stand up first.
You mentioned that, well, okay, so you're using heat from the sun to kill bacteria. How would someone, let's say you gave me the system, I walked outside and I started using it, how would I know when it's done?
There's a certain time duration that we're going to go with. And basically, based off intensity, it's going to be a time duration. And I think we were also talking about having our valve.
Yeah, like either like a thermometer or on the valve. Like it'd be similar to having the thermal control valve, but it would just be like you'd actually, instead of having it loop through like as a shutoff, you could just read it on there and be like, because pretty much 140, 150 degrees Fahrenheit is enough to meet all of our bacteria killing restraints. So as long as the water can get to that temperature, we kind of just know that, okay, we should be good. So that's what testing is going to do.
Do you have to maintain 140 for each duration of time?
The temperature depends on the time exposed. For example, a higher temperature, there's a certain temperature that will kill everything instantly, or almost instantly.
It was called rapid killing. Was it
So
like
140
was it 130? So yeah.
Oh, okay.
So as long as we can get to that temperature in our 5 to 6 hour period over the day, then you wouldn't want to go to the well early.
We're just hoping, really quick, we're hoping to model it after the sodas bottle idea. That's kind of where we're coming from. So for them, it's super simple. Fill it up in the morning, put it on your roof. At night, if it's full of sun, it's done. If it's cloudy, 2 days. So we're trying to make it as simple as possible. But at the same time, we'd also like to have some double check, safety features of thermal control valve or something like that.
Then a follow-up question. Have you guys, obviously it's going to come out of this thing really stinking hot, so it's not ready to drink. Is there some sort of like secondary storage that comes along with it?
We are considering that. That's slightly out of the scope of our project. The idea of specifically our project was really just the purification aspect. But yes, there would have to be a tank for it because it's purified. You empty it, and then that way the next morning you're able to fill it up again. So the storage tank isn't the actual purification.
Last semester we had one actually on it, and after re-meeting with the client, it was like, that's not a worry for right now. But yeah, you wouldn't go up with a cup and just drink out.
Unless you like hot water.
You like you're making hot chocolate.
Yes.
So, this is your presentation. Progressed quite a bit, so it's pleased to see that. Could you clarify what components of your prototype are contacting one?
It is just the plastic. Strictly plastic all around, and then the water, the air insulation gap on top.
Water would be in the black area.
And that black area is made of,
It's black acetyl plastic. I didn't say it in our presentation, but it has a very low absorption rate for water, or it's very non-absorption of water. So it's a plastic that's used a lot in electronics because it doesn't absorb water. It doesn't obtain moisture.
I see, do you know, at all, if it's ever been used in a water application?
Drinking water.
Drinking water
Yeah,
application, no?
I don't think so.
I mean, I don't think we know.
A quick tip, it always kind of helps. McMaster-Carr has so much information. You can start looking at plastics. You can try to force acetyl, try to force FDA, and it might spit something out. You might learn that way. It's always a good.
Well, that's been like parts were ordered before we even did that part. You know, I was telling Mark, like I never even heard of that program before. So I mean, we can look at it now for sure.
Yeah.
I don't think we should change the plan, that's fine, but you already purchased it. It's a consideration that you'll need to think about. And in the United States, there are formal regulations for material leaching that come in contact with potable water. But we're not designing this for the United States, we're designing this for how rural areas or countries, probably, somewhere where it makes sense to have this kind of system. So whether or not it needs an FDA, that'd be nice to know if it did, and then I wouldn't have to worry about it. So we might want to do a region, study that material.
That'll be interesting.
Yeah, sure.
Yeah, I'm just curious. So I don't think you have to change. We should check the beach. It's already FDA approved. That's great. If not, I also have a temperature recording thermometer used to take temperature measurements on the top. I haven't hooked it up, so when I let you use it, you guys can figure out how it works.
We looked at a few also. We didn't purchase any or even put them on our parts list, but we had looked at a few just to see like what options would we have. You know, should it be interior, exterior?
I don't know if it'll work for you, but I have one. I know what drawer it's in. But you guys
Just
figure out
prototyping
how
all
to
about.
Did you do any stress analysis? You said 40 liters of water is heavy.
It was 80 pounds.
So is the plywood strong enough to?
We're actually, we're not actually doing a frame and then a sheet of plywood on the bottom. We're gonna use 4x8s, 2x8s, excuse me, 4x8 would be close, 2x8 underneath, and that way it'll provide a little more rigidity to it.
Yeah.
And then we're using a 4-leg system that's not completely on the exterior corners, but it's scooted in a little bit, so it doesn't sag.
Yeah, so
Like
it's
stuff is
supposed to
stressed now, so. But we figured that was a better idea to use the 2x8s instead of a piece of plywood.
You've got, is there a way you supported that this supports 5 households? That is that calculation? You're showing me dimensions.
It's 40 liters of water. Well, we looked at the average water used by household per day by some governmental organization. They give us an estimate, they did a simple calculation to find that 5 households with an average family size, it would be about 40 liters of water a day.
But as far as it being included on the slide, no, that calculation was not shown.
And this whole county?
40.
This whole.
Well, our prototype one.
The prototype only will
Yeah,
count.
yeah.
This system.
This is, yeah, the papers and all
Yeah.
that. And if you go to the heat transfer calculation slide, it looked like your plot was 8, but then I didn't see any projections. equation, so I don't understand how to put the equation in this block.
I will take this part. After doing calculations through twice, they continually keep getting lost. So all parts were ordered based on calculations made that were gone over with our client and the original calculations done with you. This plot was just to show that it was an asymptotic logarithmic relationship between the air gap and as the air gap increased, it continued to get better and better, but it was like, you know, the bigger we make it, the harder it is to ship. So we just picked 2 inches was, you know, it kind of had this very, 1 inch, shot up, 2 inches was about right here. So it's like, let's just choose 2 inches. So this graph isn't actually ours. It was just a visual relationship between that and this equation for our thermal conductivity from water to air relationship. So as far as the rest of the again, all parts were ordered based on calculations made that were gone over before ordering. However, I've lost the whole data sheets that I worked probably 6 hours on in total twice now. And it's very frustrating, but
So this
I take that on myself.
This is a Google image for the diminishing returns.
Exactly.
Okay.
But these were the 2 main calculations that were used for that exact purpose. I mean, this was, our original one was done on Excel from 0 inches to 5 inches with I think 1/2 inch intervals. And then we chose 2 inches based on the diminishing return value.
All right, well, thank you very much.